Welcome everybody, and welcome to a new semester and to Physics 5429 and /9429. So this is a course which is at the master level and the PhD level. So some of you will be doing the PhD variant, and some of you will do the Master of Science variant. There's basically no distinction between the two variants. In the beginning today, I'm just going to give you a kind of overview of what we are thinking of doing in this semester. But first of all, a great welcome to everybody. As I said in the email, the lectures will always be recorded. So if you don't have the possibility of being here, you have always the chance to take a look at the video later. And for those of you who want to attend directly, I mean, there's a Zoom link. So in case you cannot be here physically, that is also another option. So I just wanted to give you first some basic messages, and some of you have seen many of these standard setups, which I tend to like, with everything on GitHub, everything pretty open. But I wanted to guide you a little bit through the basic philosophy of this course. So this course was originally something which we call a self-study course. But then there were so many people taking it that we decided to offer lectures. So we will have lectures at this time of the week. And then right after, we are going to have lab sessions. So we offer, although this is not in the weekly schedule, we have lab sessions from 2 p.m. to 4 p.m. So if you wish to hang on and discuss with us, I mean, feel free to do so. So this is not in the weekly schedule, but we decided to do so because there are so many people actually working on many different projects. And then we decided simply that this is something we want to have. So this room has been reserved for that purpose till 4 o'clock today. Now, for those of you who have been at the University of Oslo, you know essentially the way information is conveyed. So you will have the official website where you'll find the essential information and links to everything. And for those of you who have not been here before, if you go to the weekly schedule, there is an option to actually subscribe to these activities, which means that you can then get an update on whether the class has changed classroom, or there are other updates to the weekly schedule, etc., etc. So if you haven't used that option, please feel free to use it. It's quite convenient. And the other kind of official channel which we have is Canvas. So this is a fully open, and you will find the messages which we put in here, but you will find the same messages on Canvas. And you will also find at the bottom here the link to all teaching material. So I'll come back to the GitHub sites. The Canvas interface is something you're probably familiar with. You will see the same announcements, links to videos of lectures, etc., etc. And this is also where you will hand in the projects. The GitHub site is this one, and this is the third information channel. So these channels contain essentially the same type of information, except that here you find all the lecture notes, the weekly notes, etc., etc., links to textbooks, and so on. So you will also find the weekly schedule, a tentative one. This is something which we will update depending on how fast we move, and also depends also on your background and your interests. So there's something I wanted to say in the very beginning, because this was defined and is defined as a kind of self-study course, which means that we want you to have a freedom to explore what you would like to explore. So there's a lot of freedom in the projects. I'm coming back to the different paths which we have, and what kind of paths we will follow in the lectures, because the lectures have to offer something. But then some of you may not be interested in those topics because you're doing something else. Machine learning and AI, as you know, are fields which move swiftly. So what was new in 2016 is old nowadays. So 2016 in machine learning is close to what we call archaeological time. So there are so many new things going on that sometimes it's difficult to catch up and say that this is what we want to focus on. So that means that we want to have this kind of flexibility in the sense that depending on where you are and what you want to do, you can actually tailor the projects in your own direction. For me as a teacher, that's also a fantastic way of teaching, because you guys are going to do things which I will never have the time to do. And that teaches me a lot. So I get something back, a lot actually. There's a limit to how much you can explore. You as a group, you are also a very heterogeneous group. You basically come from all departments at the College of Natural Science here, Matematikfakultetet in Norwegian. And we even have people from humanities and social sciences. So that means that sometimes it's a little bit difficult to find the right level. But we will see how it moves on. So as I said, for those of you familiar with GitHub as a version control repository and Git as a version control software, you can obviously download all this material by just either using a graphical user interface, a GitHub desktop. You can download the zip, or you can just paste it in, and in a terminal window, just run the Git commands in the terminal window. So I'm actually assuming that everybody's familiar with Git as a version control software and GitHub as a provider. Is there anyone who's never seen this before? Good. So this has moved swiftly, actually. 3 years ago, half of the audience would not be familiar with Git and GitHub. So if you peep into the doc folder here, you will find the weekly notes. I mean, the blackboard or whiteboard notes will be posted there as a PDF. So you can look up my ugly handwriting if you want to. Under the pub folder, you will find the weekly material, either as a Jupyter notebook or as a PDF, and you can use the format you prefer. When I'm running codes, I will typically use the Jupyter notebook, but I will switch between the PDF and the Jupyter notebook. You will find, if you go back there, you will find literature here, and you will find some textbooks. And I've tried some of the textbooks which we have actually available for free online. So you can download them from the university library. So you don't need to pay for them. And essentially all the textbooks which we are linking to, they have GitHub sites, companion GitHub sites, where you will find Jupyter notebooks for every chapter in the textbooks. I mean, what is missing is the full text, but you will find the essential Jupyter notebooks. So you can actually use them as a starting point. That was a little bit about practicalities. The Zoom link is here. We will keep that through the semester. And what I want to do now, unless you have any questions, is to say a little bit about what we plan to cover, if that's okay. Yeah, questions?
Right. It seems like I applied kind of light of this course. And as I understand, number of seats is limited. Is this going to be a problem?
No, no. So we try to accommodate everybody. And we've roughly been something like 40, 50 every year. And the thing is that many of you, being either PhD students or master students, sometimes you just join via Zoom. Sometimes you prefer to work by yourself. I don't get offended if you don't come here. So you have to find your own way of working with the material. But just keep in mind that everything is available and you can use it as you want. Feel free to use the notes as your own lecture notes. Build on them. If you find typos, etc., just send me a mail. So, but we normally have not had problems with seats. But you see, this room is a little bit limited. So in case we become 50, 60 in the lectures, we would have to change room. I know. Yeah, no. So this is something which we always tweak. So the administration of the physics department is extremely flexible. It's always been. Any other questions about practicalities? Okay, so let me now switch over to the material for this week. So there's going to be some kind of general blah blah from my side. I don't know if those online can see properly the notes here, the slides which I have. Yeah. Sometimes I have to take off these ones because yeah. So the first project has a deadline tentatively March 21st, and the final one has June 1st. So I'm coming back to this a little bit later now. So if you look at the basic topics which we're going to cover today, one of the things I actually wanted, and I'm going to ask you this many, many times, is whether we could, if you have the possibility to stay a little bit after the lecture into the lab session, because then we can discuss the different paths for the projects. And that gives me some input, and you should send me input, what you want to do. Because then I can try to finalize different types of projects. Okay? So the emphasis here is on deep learning methods, discriminative ones and generative ones. There's one reason for that. These are popular methods, like diffusion models and so on, which enter many of the modern, let's say, drawing methods or designing data for experiments, etc., analyzing data and so on. So these are methods which are extremely popular, but there is obviously a limit to how much we can cover in 15 weeks. So that means that the path I've chosen is to focus on first the standard deep learning methods. So that's going to be something we will use the next 2 to 3 weeks to repeat things which some of you have seen already. Or if you've seen it, you may have forgotten some of the details. So we will just remind ourselves a little bit about neural networks. And then we are going to dive into the mathematics of CNNs and RNNs for time series. We are going to discuss autoencoders. And then when we've done with that, that will be the first half of the semester, roughly. In addition, if we have time, we may look at graph neural networks if we have time. But then we dive into generative methods. And I will try to say a little bit about the differences between these two in some few slides from now. This first week, there is for those of you who have studied neural networks, it can be useful to look at the text by Goodfellow et al. You can find the text online. If you just clicked on the Goodfellow there, the chapter 6 and 7 give you a basic introduction to neural networks and the essentials. And then Rashka, which is a textbook many of you have used, is extremely useful when it comes to coding, in particular if you want to use PyTorch. So in this course, you are free to use software like TensorFlow, PyTorch, scikit-learn, obviously. But then there are also people who want to write their own code from scratch. And this has been a path which we like to have, because there are always people who want to write their own recurrent neural network, their own CNN code from scratch. And that's typically a 1 semester project. And then you just do one project. I'm coming back to these options. So the videos of the lectures will be posted after the lectures, obviously. So we have lectures, and then we're going to have these exercise sessions today from 2 to 4. And the plan is actually to have 2 main projects. And I'm going to say a little bit about it. But then I actually wanted, if you have the possibility to stay a bit longer, or just send me an email about what you would like to do. So there's no exam, only 2 projects. Alternative is a long project, a semester-long project. So all info, you find it here. So we are going to cover roughly these methods. This is the first half of the semester. It depends on how fast I move. I tend sometimes to be a little bit slow. So maybe we would have to drop 1 or 2 of them. That depends on how fast we move. And it depends also on your background. So the next topic is actually about generative methods. And we have the basics. The basic first method we're going to look at is a Boltzmann machine. And these are also called energy-based models. We are going to look at diffusion models, variational autoencoders. Actually, the person who wrote this algorithm called Adams, which is used in gradient descent and which has more than 200,000 citations, is actually the person who developed variational autoencoders, which has something like 50,000 citations. So it's a little bit intimidating, but it tells you how popular many of these things are. And then we have GANs, and we may say something about autoregressive methods if we have time. And this is also very important for people interested in LLMs. So last year we had a group which actually wrote their own LLM code. So we also have another topic which forms the basis for a project. And this is for those of you who are differential equation aficionados. And that is the field of physics-informed neural networks. So it's not only physics, because this is mechanics, it's geoscience, but it's actually you modeling a neural network with the boundary conditions and then optimizing that type of problem. And this has been extremely successful in many fields in science. So this is a typical path which we have for the projects as well. But we will not cover that in the lectures, except for the standard differential equation part, which enters neural networks and recurrent neural networks, and also autoencoders. But the pins part will be something which you will have to work on independently. So there's also a very hot topic. And the reason why I don't put this in is that in the fall semester, we have in the Department of Mathematics a course on Bayesian statistics, which I highly recommend. So that's a fall semester course, actually. But every year, there's been somebody who's been interested in Gaussian processes. I will come a little bit back to why these things are so interesting for us to do science. Because the standard machine learning approach, like typically with a neural network, is something which in statistics is called a frequentist approach. That means, practically, that we are less interested in the probability distribution. We take some data, we fit a model to the data, and then we try to do the best possible fit. And then we want to use this model which we have fitted to make predictions. So it's you finding the correlations and making predictions. Now, when we do science, we also want to estimate the errors of the parameters of the model. This often means that we would like to have a probability distribution. So this goes back to generative methods, which we will cover here, but we will have an overlap with Bayesian statistics. So Bayesian statistics deals with you fitting a probability distribution to describe the data. So when you have a probability distribution, you can generate new data, you can make predictions, you can find correlations in the data, you can look at causation, which means what is the likelihood of B given A, and you can estimate errors, because you can calculate things like standard deviations. So a Bayesian approach is the other type of approach which is very common in this field. And every year there's somebody who wants to look at Gaussian processes. So this would also be a topic for self-study, although we will cover the basic philosophy here when we look at generative methods, like Boltzmann machines, variational autoencoders. Actually, variational autoencoders are an example of Bayesian statistics. I don't have any plans for reinforcement learning, but this is also a possibility for those of you who want to explore that. So I want to keep this kind of flexibility. Obviously, we shouldn't stretch it that far that, well, I don't care what we are doing in the course, I just want to do this, although it doesn't overlap at all with what we have outlined. So it has to be, what you do has to be within the general family of machine learning methods. Okay? Okie doke. So the project paths. So we have in general had something like 5 different options. So one is the plain coding path, and every year, so last year we had 2 groups. which programmed their own convolutional neural network. One group which did a recurrent neural network from scratch. They didn't do the long short-term memory variant of it, but they just did the plain recurrent neural network. We are coming back to the mathematics of these networks. And a group last year were actually looking at a simpler large language model. So these are typically, if you want to venture into that one, these are typical one semester projects. So just one project only. So feel free. And also another important thing is actually to, you should also feel free to set up groups. We normally recommend people working together. That makes life much easier and one learns a lot. So the second path is actually a path which we can begin with when we start with neural networks, where we start looking at the solution of differential equations. Those of you who studied physics SDK 3155, 4155 may have done a project on differential equations. So this is a path which is tailored really to people who have an interest in solving differential equations. And that means that we could have the first part of the first project, which deals more with studying the solution of a set of differential equations with a neural network setup. And then the second project could be one where you try to implement pins. Alternatively, you can bring together two projects into one and have a longer one where you just explore pins and more advanced pins methods. So pins is physics-inspired neural networks, but one should actually call them physical sciences, or it's actually beyond the physical sciences, because this is something which you could actually call a solution of differential equations with boundary constraints. That's perhaps a broader and better way of saying it. So these are the two first ones. Then there is a third path which follows the lectures here quite a lot. In this path, you could have a simpler data set. Suppose you could take some images or other types of data sets. And the first part, you would run convolutional neural networks and autoencoders on that data set. Then in the second project, you would implement generative methods. So when you do this, you can decide how much you want to write from scratch and how much you want to do with libraries. And online and in many of the textbooks which we have, there is lots of codes which you can reuse and adapt to your problems. So this is a path which path 3 is the one which is going to be the closest one to the lectures, together with also the pins part. Now, then we have something we call the own data path. So some of you have data from experiments or other type of data. So like the year before, there was a PhD student from the Norwegian Life Science University who had data on banana flies and wanted to find deeper patterns in the genetics of banana flies. I think that was a fantastic project. And that person used then different machine learning methods to analyze the data set for that person's PhD. So that's one possibility. And every year we have different groups of people who have experimental data, other types of data they want to analyze with the methods which we talk about or other methods. So this could also be just one standalone project. Or you can split it in two, where you analyze the data with discriminative methods, and then you move on and use generative methods. So this is, again, something we can keep discussing, but we should try to nail down the different types of projects by the end of next week, so that you can get started. And you don't keep lingering on till the semester is almost gone, right? And then panic kicks in, and when panic kicks in, we often get totally, dumbstruck, and we don't know what to do, actually. At least I do. And then we have something which we call the Bayesian path, which is not covered by the present lecture material, but feel free to explore that path. Then I know that, so I've been together with colleagues, we've been developing another method, which is called parametric matrix models, which I'm pretty proud of. And if somebody wants to explore other methods, I mean, we can always set up a path which does that. So this number of paths which you see is not limited to 5. So feel free to come with input. And we can always also design paths which match your thesis, your master thesis topic, so that gives you, how to say, a better start in your thesis topic. If you're a little bit uncertain, then you can explore things which are related to your thesis and see whether you like it or not. I hope there's not too much flexibility. I love having, I mean, this is the way I love to teach, because it gives so much back, because everybody explores different things and there's a limit to how much you can do yourself. Yeah.
Can we combine this concept and positioning and paper?
Oh yeah. No, so you can do that. We also had many people who have, I mean, it's not a must, but some of the projects end up being scientific papers. Now, I teach actually 2 other courses in the spring, and one is on quantum machine learning. And there we always, if you're taking both, we always offer the option that you can merge a project here and a project there. That's also another possibility. So I will come back to this. So you can actually read some of these things yourself. Yeah, this is actually one thing I wanted to point out. So this university actually suffers a little bit from a lack of courses on the mathematics of deep learning. And every year there's somebody who wants to explore more the mathematics of deep learning methods. That's also a possibility. So we have courses in statistics, but they often had a statistic approach to the courses, and there's been less on the underlying mathematics. This is actually an emerging field in deep learning. So this is something, if somebody is more mathematical inclined and wants to explore that and wants to define a project, this is also another possibility. However, as I said, I mean, we have to say something during the lectures, and the lectures will essentially then focus on what we call as generative models and discriminative models. Yeah, I'm just describing the different parts, so you can actually read these a little bit yourself a little bit later. It just gives a little bit more information about what you can do. So I'm not going to repeat everything. There is also a final path here. So some of you may be following a course which is called IN 4200. So one thing we had there was previously, some years ago, was a possibility to study the implementation of these algorithms on GPUs and CPUs. So the high performance computing part. And 2 years ago, we had somebody who actually did a project on that. So this is also an option. And there you can actually take what you're following, what you're seeing in IN 4200, which is essentially high performance computing with the parallelization. I think it's mainly on CPUs, less on GPUs, but this is also an option. So that would be more what we would call a plain computational science project. Yeah.
Sorry, because I am actually following the course IN 4200.
Yeah.
And the problem is on Thursdays, there are lectures between 2:15 and
Yeah.
4 p.m.
Yeah.
So,
I know. We haven't been able to catch all birds with one stone. So I'm sorry for that. But we can always have individual talks later on if you're stuck with projects and so on. Anyway, so if you cannot attend here on a regular basis, you can always watch the videos. Okay. So these are the books which you can all access. So Rashka's book, you can get it from the university library if you're on IP address of the university. And this is a book which I find very handy when you look at the discriminative methods. So both for CNNs and recurrent neural networks and autoencoders, this book is excellent. So the first half of the semester is extremely well covered by chapters 11 till the end of the textbook. It also has a chapters on transfer learning, so which some of you may find very useful. And it's a pretty new one. Then there are also two new books, one by David Foster, which looks at these generative methods, Boltzmann machines, or actually energy-based models, and several other methods, also advanced ones. And the book, every chapter has Jupyter notebooks with very detailed examples. So Sebastian Raschke et al. Runs in PyTorch. So how many of you are familiar with PyTorch? Yeah, so you can use the tools you want. We also had people writing things from scratch in C++ and Fortran, actually. We had one in Fortran some 3-4 years ago. Some people prefer using Julia. Feel free to do that. I am a little bit rusty in Julia, but I can help you with Python and C++. And if there are some Fortran dudes here, I can also help you there, because I started programming actually in BASIC and then Fortran and then Pascal, C++. Yeah, and Goodfellow, Benjo and Cobill, that textbook is now old. It's back from 2016, but it gives a very good introduction to generative methods. So in the lectures for the more mathematical aspects, I will use chapters from this book. And every week, I will give some reading suggestions, which align with the material we will cover. So, oops, it's supposed to be test yourself. Okay. So now if you look at the questions here, I actually wanted to, how to say, we're actually going to, when we go into neural networks, we are not going to repeat all details. So we are assuming that you have some familiarity with it. If you have not, there is a threshold you will have to be able to jump over. We will help you, but we will start rather quickly with the basic mathematics of neural networks. And you should feel free then, through the examples which we present, either to use PyTorch, TensorFlow, or write a code from scratch. We will show you examples of all these possibilities, but we will not go into the details of neural networks in the same way as we did in FYS SDK3155, because many of you have actually programmed a neural network. So if you look at these questions here, let me just see, if you look at question 1 here, so how many of you think you can answer that question with just some quick repetition? Okay, that's a good fraction of you. What about question 2? Yeah. Question 3? That's a good fraction of you. So these are essential elements of a neural network. So I just want to see where we are so that we can tailor the lectures properly, and so that many of you won't find it boring. That's also important. And that you get something new. If you look at question 4, how many feel comfortable with that one? Yeah, okay, still a good fraction. What about 5? So this is a big problem in neural networks, which is actually related to the question about activation function with exploding gradients. And you will see that when we come to recurrent neural networks, exploding gradients will actually ruin the training. And there are many different ways of dealing with that. Yeah, vanishing gradients, exploding and vanishing gradients. Yeah, I should have written vanishing as well, sorry. Good point. Are you able to name type of hyperparameters when you tune neural networks? Yeah, I see. Okay, excellent. So who could describe the architecture of a CNN? Yeah. So this is something we will spend more time on. We'll go also a little bit deeper into the mathematics. And let me just skip this one because we talked about the vanishing gradient. Is anyone who could say they could answer question 3? Yeah. Any good answers to that? Somebody who wants to answer the question? Yeah. Yeah, exactly. Exactly. That's, yeah. Yeah. That's also. So there could be many reasons. Excellent. I'm going to skip 4, but I wanted to hear a little bit more about 5. So if somebody wants to comment that one. Yeah. Yeah, that's a good point. Yeah. Yeah. Yeah.
It's easier to use a sledgehammer.
Yeah, that's more comments about the 0.5 here. Yeah.
It was something about the fact that when it comes to unsupervised learning,
Yeah.
like when it comes to dividing data, you just simply cannot use those simpler methods. And
Yeah.
you have to use several layers methods that is deep learning.
Yeah. That's so for unsupervised learning, these methods are actually really good, actually. Yeah. But yeah.
Basically, putting way more parameters than
Hmm.
you need.
Yeah.
And then assuming that some subsection of that will actually fit.
Yeah. So I have another take on it, which is my favorite one. So these are all excellent comments. So my take on is that a neural network or deep learning method is a universal approximator, which means that, and you will see that when you solve differential equations, if you solve a differential equation with low dimensions, the neural network will provide you with an error, but it will never be able to beat the standard, let's say, partial differential equation solvers, which have been really fine-tuned. However, when you go to many particles and many dimensions, then what you will often see is that the error stays more or less the same. But then the traditional methods, which often tailor to, let's say, 2 or 3 dimensions or few particles, they cannot compete with a neural network as a universal approximator. And this is something you will see. So those of you who are familiar with Monte Carlo methods, like Monte Carlo integration, when you use Monte Carlo integration, if you want to compare that with, let's say, a highly streamlined Gaussian quadrature method for a 3-dimensional integral, the Monte Carlo method will never be able to beat that when it comes to precision. But if you go to a 10th dimensional integral or higher, the Monte Carlo error stays the same, which is 1 over the square root of number of samples. And that's where they become extremely useful. So when you have a high dimensional problem, that's where the neural network as a universal approximator really kicks in as an advantageous method. So this is something which I am interested in because I often solve quantum mechanical problems with machine learning methods. And then the dimensionality problem is actually the big problem, the rising or exponential growth of degrees of freedom. So if I look at an atom like neon, atomic neon, with only electrons in 3 dimensions, that is a 30-dimensional problem. And there is no way you can solve that with standard differential equation methods. You had another take here. Yeah, yeah. But these are also things we can discuss in the lab sessions as well, right? Okay, I have another one, testing where people are, which is also a very important part. We don't need to take all of them. But if you look at one, so how many would feel comfortable with answering that one? Yeah. And which would be the standard mathematical method? What is the starting point, essentially, which we use for all the approximations later? Yeah. Newton's method. That's where we start. So mathematically, we're actually doing a Taylor expansion around the optimal values. which should reflect the minimum of the surface we are optimizing, which represents all the parameters. And doing that Taylor expansion, we truncate at the level of the second derivative, and that leads to Newton's method. Yeah.
Why we are using the one like halving the intervals? We keep on halving the interval
because it's going to be much too slow. Yeah. So at the end, you're training millions of parameters. If you're doing a large language model, you're training trillions of parameters. And then you want something which is fast. So it's always this compromise, which we have at the end. It's you who decides and settles for the compromise between the number of cycling or CPU cycles you want to spend and the precision you want to achieve. That's you who decides at the end. Why don't we use Newton's method directly? Yeah. 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 But what about if you think technically? Yeah, there's one in the back there. Yeah.
Okay. Well, there's a Taylor expansion and you get the numerical dispersion.
Yeah. Yeah.
It's a big issue in the use.
Yeah. More reasons you could think of? Yeah. Yeah, that's yeah. That's another good point. Something else which comes to your mind? Yeah. Yeah. And what about the second derivative? It's when rephrases a matrix is a name you will encounter in the statistics literature, the Hessian matrix, and you don't want to invert that one. And that's where these learning rates come in. So like this momentum or Adam, which I mentioned had more than 200,000 citations now, back from 2014. And there you actually tune these parameters. I'm not going to ask that question, but if you look at the fourth question, why should we use stochastic gradient descent instead of plane gradient descent? So we have the same people answering now. So we have somebody in the back there, right? Yeah, you have your hand up, right? Yeah, yeah. Excellent, excellent. Anyone else who wants to add to that? Yeah. Yeah, excellent. This is very good, actually. So you can look over these questions, and then I'm going to leave this one so we can move on a little bit. But take a look at them, and then ask yourself if you feel familiarity with it or not. So if we look at machine learning, we will essentially deal with supervised and unsupervised learning. And when we come to many of these generative methods, these are also methods which are very well tailored to unsupervised learning. So even neural networks can be used for unsupervised learning, even if traditionally people say that this is something which is really tailored to supervised learning. You will also have a difference between discriminative and generative methods. So I'm going to quickly go through some of these things which many of you are familiar with. So we will discuss classification types of problems. We will look at the standard regression type of problems, and we will also say something about clustering. These are things which we will also discuss here. And if you now look at the central methods which we will cover, we will essentially stay with point 1 here. That's where we will stay in this course. Bayesian statistics, as I said, is an option, but you have a regular course which runs in the fall semester on Bayesian statistics, which is highly recommended. Dimensionality reduction is something we will discuss in connection with autoencoders. So this is something which is called the PCA, and we will discuss that together with the discussion of autoencoders. And we will not say much about these other methods. We may say something about transfer learning or things like that, but the focus will be on PCA, point 3 here, and also on point 1. So I'm just going to dive into a figure here. So generative models. And to give you the distinction, the rough distinction between generative models and discriminative models. So a generative method, like a Boltzmann machine or variational autoencoders, is a method which is trained on data, but what you do is that you fit a probability distribution. And then you can use this probability distribution to generate new images or new data. And this is something which is much closer to what we are often interested in when we do science. So one thing is to get a prediction by the standard discriminative methods like a neural network or linear regression, and then find correlations in the data. But we also want to look at causations, and we want to estimate the errors which we make in a given model. So we would like, for instance, to have an error estimate on the parameters which we optimize. So having a probability distribution is something which is extremely important. And this is, in my own research, this is what I'm mostly interested in. However, a neural network, which is normally thought of as a discriminative method, can also be thought of as a generative method. If you solve a differential equation with a neural network, you're just optimizing the difference between the left-hand side and the right-hand side of the equation. And you generate a new solution. So the solution you generate is a neural network, and you can use that one to produce new points. So a neural network can also be seen as a generative method. And if you do quantum mechanics, if you square the neural network, you have a probability distribution. So these are, it's the kind of border between this method is not always that strict. So I'm going to skip some of the text before we take a small break now. And I just wanted to say a little bit about the standard discriminative methods, which many of you have encountered. And let me just shrink a little bit the dimension here, so it fits into. So if you look at a discriminative method, you would then train on images as an example. So you could have paintings of Van Gogh. And if it's a Van Gogh, you label that with 1. If it's not, you label it with 0. And then you train a model to recognize Van Gogh paintings. And then you plug in data which has not been seen by your model. And then you want to make a prediction, and the prediction accuracy, this 0.83, that could be the accuracy of your model on data which was not included in the training. So that's a typical example of how you use a discriminative model. You just discriminate between cases. And then depending on the type of applications, you may be more, Yeah, that would still stay within a frequentist approach. Yeah, exactly. So as long as, so if you think of machine learning, I mean, there's been traditionally a kind of split between frequentist and Bayesian approach. I find that split artificial because I'm interested, I'm like Winnie Pooh, I want both milk and honey. So I want both to make predictions, find correlations, causation, and also to be able to estimate errors. So generative methods are very appealing to me, for instance, for the kind of science I'm doing. So this would still be with what you say, a discriminative model. So let me just show you a little bit before, and now we can take a break here, because this covers some of the methods we will discuss when it comes to generative methods. And after the break, I'm going to give you a little bit deeper overview of some of these methods. So the problem here, when you see density, this is a short for probability distribution density. So it's a probability. And some of these methods treat the probability in an explicit way. And then you can have an approximate density. So variational autoencoders is like that. Boltzmann machines is an example, energy-based models. How many of you are familiar with the Boltzmann distribution? And you know that that goes like the exponential with minus an energy, right? Now, this energy has lately been changed to be a neural network. And this has been proven to be, or been shown to be an extremely efficient method. And this is something which we will also discuss. Energy-based models. We have diffusion models. So me as a physicist, I see many of the kind of physics way of thinking which pervades many of these models. So this is me putting my arrogant physicist hat on top here. But this is a field which is being developed by so many different disciplines. We have tractable densities. We will say a little bit about autoregressive models. And then we have the implicit one, which is given by generative adversarial networks, which we will also cover. So we will say a lot about some of these central generative methods. Okay, this was the kind of first survey. Before we just go back and remind ourselves a little bit about some basic machine learning and some further links. Okay, so let's get started again. And so what I wanted to give you now is a quick overview of, so if we just, if we look at the type of problems which we have. So I wanted to remind you, everyone here, about the kind of basic things which are going to enter everything we do in machine learning. And as you know, one of the basic ingredients is the data set, which we are going to study. And depending on what kind of path you choose, one path which people have used sometimes is to train a neural network on solution of differential equations. So just to give you an example, what you could do then is actually to use a standard differential equation solver, like a Runge-Kutta method, if you're familiar with that. And then you would solve a differential equation up to a specific time. That would be your training data. So the input would be the previous position at a given time, and the output would be the next position at a new time. And then you go on like this, on, and you train your network on all these positions and times. And then the network you have trained is something you can use then to make an extrapolation and prediction to times which were not included in the training. And in that case, you can actually compare that with the solution from your favorite numerical method. This is one way of using it, but it's actually not the best way of using it, because that means that you need to have something which has been pre-trained on data. But that's something which we have used also in the analysis of time series, because it's a way to have things started and to test it against something which is well known. And then you see that the algorithms are functioning, and then you can start applying this to more complicated problems. If you want to do, let's say, a physics-informed neural network. So the data set is something which you simply need to have. And then you need to have a model. And in our case, the model is going to be a neural network. So when you do typical linear regression, the model is the function you want to approximate. So this could be a function of cosines, it could be a polynomial, or whatever you think is most relevant. But now your model, since we are essentially going to deal with deep learning methods, your model is going to be the architecture of a neural network. And we are coming back to these elements just to remind you of that. So what you would be training then would be on a specific function, which we normally call the loss or the cost or the risk function. And that's the function we end up optimizing. So a little bit later, I'm just going to remind you of these basic elements by equations. And we want to optimize this function, which essentially means minimizing, to find the optimal parameters, which in this case would be some alphas. And this is in general a multi-dimensional problem with thousands or even millions, trillions of parameters, which we want to find the best optimal representation of. And then at the heart of everything, there is a optimization algorithm. So typically, just to quickly remind you of one of the simplest, I hope you don't get offended if I remind you of some of these simpler things. This is just to have everybody more or less on the same page, because I'm going to reuse this language again and again and again. So the input data is something, if you have a vector of observations, this could be the velocities of something. The y's could be the cross-section of something. So you could have some particles impinging on a material. And then you measure a cross-section, just to give you an example. It could be any other thing which you find relevant. So the x's could be the pixels of an image. And the y's could be whether this image is a Van Gogh or not. So that means that the y's would be 0 or 1 if you have a binary classification problem. Okay? So this, I'm just trying to reboot your memories from before Christmas. So I'm not insinuating that you have a goldfish memory like I have. So my memory needs constant reboots. So feel free to do that because I tend to forget things. Some people call it age. But the typical thing we often do is then if we do a regression type of problem, which essentially means that we want to fit a continuous function. And then this function, we assume that that exists, and there may be some noise. And I guess many of you have seen this before. And typically then, if you do a linear regression, we would have a linear dependence on the parameters, the unknown quantities. And this X is a way by which we rewrite the input data. The theta are the unknowns, and this is our model. So the thetas could be the parameters of a polynomial. And then, if you're doing a regression type of problem, one of the most standard functions is the so-called least square error, or the mean squared error, where we simply emphasize, in a certain sense, the deviations from the value we want to observe. And this is normally rewritten in terms of these parameters as this function here. And then we take the derivative with respect to thetas. And just to quickly remind you, we have in that case, and we often call linear regression for low-level machine learning. That's my way of naming it, simply because here, many people may ask, where's the machine learning here? This is just a linear algebra problem. You invert a matrix, but we are learning the parameters by implementing this algorithm. So we are implementing the algorithm, and then the machine learns the parameters by solving that equation. So this type of methods are always included in every textbook on machine learning because it serves as a kind of a entry point, and it's easier to understand. You have an analytical expression. You need only to invert a matrix, and you can also make a nice statistical connection here. You can actually obtain the same equation by assuming that the points y are described by a Gaussian distribution. And then you can actually optimize the Gaussian distribution and obtain exactly the same practical equation. So linear regression is very nice because you have analytical expressions, but you can also give it a statistical interpretation. And you will see it essentially in all textbooks in machine learning. But normally we don't use it because it depends very much on your capability of inverting that matrix. And if this matrix is large, so if you're doing genetics and you want to find which parts of the DNA may be responsible for one type of tumors, you may have millions of features. And that means that that matrix will be a million times a million matrix. So that means that there is a limit to when you typically use these methods. But if you can use them and they give a better result than a neural network, which they sometimes do on simpler functions, there is no point in using a heavyweight method like deep learning methods when you can do something much, much simpler. This is at the end, it's you who has to make these choices. You have to make these choices, not has. I mean, yeah. Okay, so the optimization problem is that one, and you can add terms to this optimization problem. So one of the typical optimization problems which you have encountered in many, many cases is something which is called ridge regression, where you have a norm 2 parameter, which you multiply with it, and not a norm 2, but you have a norm 2 of the unknown parameters multiplied with what we call a hyperparameter lambda. Now, how many of you are thinking of doing pins? Well, it's a good fraction of people. Excellent. This is excellent. So we can already set together a group of people who want to work with pins. So maybe you could stand up actually, if you who is doing pins, who wants to do pins. So we have, and then you can see each other. And this, yeah, so we have 1, 2, wow, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. So we have a good possibility of setting up working groups. So feel free after the break, after we're done with the lecture now, to see if you have some points of convergence and if you would like to work together. I mean, we are not forcing you to work together, but it's a very, how to say, it makes life easier. And also, some of you may be very good on mathematics, some may be good on computing, etc., and you learn from each other. But for those of you doing interested in pins, actually what you end up with is an optimization problem where you bake in the boundary conditions in addition to a function like this one. The first function is actually a rewrite of the mean squared error. So you would bake in the boundary conditions so you get a feedback from the environment. And then you optimize a problem which is different from the standard way by which you would solve differential equations, by taking the difference between the left-hand side and the right-hand side of an equation. So essentially pins, if you think of this from an overarching point of view, this is what you end up doing. And then we have a lasso regression, which is just another type of a norm. So this is called a norm 1, where the norm 1 is actually given by the sum of the absolute values over the parameters. And these are typical hyperparameters which you would add to your optimization problem. And that gives you more flexibility because you can tune these parameters here and perhaps get a better training error and also a better error on the test data and validation data. So I wanted to give you other examples before we start reminding ourselves about neural networks. So I wanted to use this day here more to get us all on the same kind of track and take the kind of bird's view on these methods. So this is actually into my own research. And what I've been doing in the last years is actually, so I've been doing many body physics with something which is called Monte Carlo methods. But essentially what that is you evaluating a multidimensional integral. In essence, that's what you do. Now, since you don't know the solution of the equations, so this is an eigenvalue problem, which I have rephrased in terms of a stochastic approach. And that means that you need to have a expression for this function. So if you have it, you basically solve the problem, and then there's no point in doing this. Now, you would solve these integrals, since these integrals are high-dimensional ones. If I have 100 particles in 3 dimensions, this is a 300-dimensional integral. You can do that. We've been solving this type of problems with hundreds of particles. But the problem is you don't have the solution, which is this psi of t. So what you can do is to replace that with a neural network. And that means that you would train this equation here with a neural network instead of this psi of t. Now, your optimization then is the derivative of this energy, or this expectation value. So what you've done is actually to rewrite a problem in terms of a statistical expectation value. And that specific equation you have then, if you take the derivative of these energies, then that is the function you want to optimize. So just to bring you back to the case we had previously, here we take the derivative of this function with respect to the parameters theta. That is the optimization. Here, I take the derivative of this expectation value in terms of the parameters which define this one. So I can tailor this one to have all the physics, all the science which is relevant, but still I'm making a guess. Now, a neural network has given amazing results. I'm just going to show you some of this. I'm not going to take in all the things here, but this is just a figure which I'm briefly going to show you, where this one, the black line here, is seen as the best possible approach today. It's called diffusion Monte Carlo, and in many body physics, that is seen as something which you mathematically can prove that if you simulate long enough, it should actually reach the exact ground state of a specific Hamiltonian. So you have to excuse me if you're not so familiar with many of these terms, but I just wanted to show you the strength of deep learning methods. So here I'm using a neural network to parameterize the function, which means that I am putting in a minimal physics knowledge into the problem. And I'm getting something which beats and always on par of one of the best methods which we have if you're doing this type of science. So this is just an application or an example of an application where a neural network now is used as a generative method, because my solution to the problem, the one which optimizes the energy, is a neural network. And I put in some minimal physics constraints like translational invariance. I put in rotational invariance and so on in my guidance for the optimization. And this is something, so typically, just to give you an example, when you use a diffusion Monte Carlo calculation, this can often take many, many weeks to find an optimal ansatz for the wave function you want to plug in. Here, you're using a neural network as a universal approximator. And you're just baking in some basic physics constraints on the system. And the neural network, through the optimization, is able to find a solution which is almost as good as methods which people have labored on for years to find the solution to. So this gives you an extreme flexibility. It's also very important because it leads to what you might call, when you compare it with other methods, to explainable AI. Because you can use the standard methods where you have a lot of insight and then compare that with a neural network and ask yourself, what is it that the neural network brings in addition to what you did before? So even though a neural network contains, in this case, the neural network has 100,000 parameters. It's actually 5 hidden layers and 100 nodes in each, plus many more parameters. So it means that when you look at the optimization problem, the parameters themselves do not say so much. So the question is, how can you interpret this wave function? And one way to do that is to use existing methods where you have a lot of insight about what they mean in terms of, in this case, the physics and the equations of motion. So this is just one example on the thousands of applications. Actually, this course is an example of that because many of you are going to do pretty different things. So when we say machine learning or AI applied to the physical sciences, the applications in every field now are so many that it is almost impossible to keep track of all of them. I'm going to skip. So one thing I wanted to say a little bit about very quickly is about Boltzmann machines, because this is something we are going to meet when we are going to discuss generative methods. And I wanted to say a little bit about the overarching problems which you're going to encounter. So a Boltzmann machine is normally something which you reduce to a restricted Boltzmann machine. That's why you have this RBM. So you would have a visible layer which contains your inputs. again, if you're doing a solution of a differential equation, it could be the positions which you have. So they are fed in. And then you have a connection between a hidden layer, which increases the degrees of freedom in the optimization process. And your parameters then would be the weights here, which connect the input to the hidden layer. And then you would have what we call biases of the visible layer and the hidden layer. So it is actually a neural network, but what you're training then is not the standard function you're optimizing, but you're actually training, so let me just move to that one. You're training a function which looks like this. And this is the standard Boltzmann distribution. This has become extremely popular, even in imaging. So for those of you who are thinking of, say, using convolutional neural networks for imaging, and let's say autoencoders, so some of you are going to be interested in that in the project, then when we are dealing with generative methods, a starting point could be to use a Boltzmann machine to generate a probability distribution, which allows you to recognize whether this is a specific type of image or not. What you would be training then is this function E, the argument to the exponential. And that function E, when we borrow from the statistical physics, is normally called the energy function. But people have lately replaced that one with a neural network. It could be a convolutional neural network or any other types of neural networks. So at the heart of all the methods we are going to discuss, there is going to be a neural network. So whether you like it or not, if you do a convolutional neural network, at the heart, there is a neural network. If you do an RNN, there is a neural network. Autoencoders are normally done in terms of neural networks, et cetera, et cetera. So neural networks is going to be the kind of central theme in this course. And in the so-called energy-based models, the treatment of this energy has given a lot of flexibility if you just replace it. Because in the first applications, what people did was to be inspired by physics, and they could use something like this. So you would train then these parameters A, B, and W, and you could have a binary model because that gave you analytical expressions for the probability distributions. So binary means that these X's and H's take two values. It could be 0 and 1, or -1 or +1. We are going to go back to this, or come to this, after we're done with the first project. So this means roughly towards the end of March, or middle of March. That's when we begin with generative methods. Now, if you look at the training here, so you see now that this E, which you have here, will depend on the parameters A, B, and W. These are the parameters you train through the optimization. Now, let me see if you can see what the bottom. For those of you online, the wireless here has been extremely flaky. So I'm actually going to replace that with my own cell phone. So just a moment, please. There we are. So that should be better. There we are. So the wireless in the auditorium has been pretty bad. So I need to restart it here. Okay. So for those of you online now, you should be able to see it. Okay. So it switched to the wireless on my cell phone and then it just went away. I'm sorry for that, especially those online. I mean, you here won't suffer, but those online will probably suffer a little bit more. And let me also see if it's recording properly. Yeah, it's recording. Okay. So if you now look at the equation here, what you have to think of is that this E depends now on the parameters you want to optimize. What could the bottleneck be in implementing a Boltzmann machine? Can you see that from the equations here? a small hint. The integrals could also be discrete sums. So the values h and x could be discrete values, but there's an infinity of them in principle. Any good suggestions? So all generative methods, which we are going to look at, whether these are diffusion models, GANs, Boltzmann machines, variational autoencoders, they will face the same type of problem. Yeah?
That's very hard to wonder it's here.
Yeah. Yeah. The root of all evil is actually in the calculation of this normalization constant C. So the problem in these types of optimizations is how do we evaluate the derivative of this quantity with respect to the unknown parameters, which we have put in to the expression for E. Yeah? Could you say it again? Yes, you would do the log on that one. So at the end, we are going to rewrite this in terms of expectation values of logarithms. And that's a way to circumvent it. But in principle, this is an infinite dimensional integral. And just think of, so how many of you have studied spin models, like the Ising model? So some of you have seen that. And there you have, let's say, a binary system with spin up and spin down. So if you have 10 spins, you have 1,054, 2 to the power of 10, possible realizations of the energies. So that means that the summation here, even for such a petite problem like 2 to the 10th, even that one is something which is going to be very time consuming. So I just wanted to point that to you, because that's one of the bottlenecks which we are going to have to face in all the generative methods. But the basic philosophy is you optimizing some function which takes this as input. And these methods are extremely popular nowadays, diffusion models, variational autoencoders, etc. And it's important, I think it's important and also interesting to have seen their applications. Yeah, this was a little bit about these types of things. Clearly, as I mentioned, one of the paths which we will not cover, but which you could explore if you want to, is about Bayesian statistics. And as I mentioned in the beginning, when you look at things like predictions and estimations, correlations and causations, these are the central topics when we are trying to develop a model and a method for analyzing and parameterizing the data which we are dealing with. So a causation is normally directional. So the A causes B, and you often want to understand what is the probability of B given A. So if you take a Bayesian approach, then you would essentially cover both predictions, estimation, correlations, and causation. If you do a frequentist approach, you normally fit a model to make predictions, and you can also find correlations in the data point. You can set up, for instance, the covariance matrix and find how correlated different features are. So I'm just leaving this, you can just read through it. It's a little bit dense, but a little bit about the kind of philosophies which we used. So if you think then of a frequentist approach, which we mentioned earlier, this is often seen as a traditional path in machine learning. And typically this learning and prediction-based tasks, they're often interested in developing algorithms that are capable of learning patterns from a given data in an automated fashion, and then use these learned patterns to make predictions or assessments of newly data. And in many cases, our concern is the quality of the predictions or assessment, but we may actually miss this possibility of finding or being able to estimate errors and understand causations. And that leads us often to the fields of Bayesian statistics. And there are people every year here who've studied Gaussian processes. We will not cover that in the lectures. As I said, these generative methods, they capture some of it because we are going to fit a probability distribution. But everything we fit is a model. In Bayesian statistics, there is also a model. And that's normally called the prior distribution, which is the model you assume on the data from the beginning. So I just wanted to flash here. I'm not going to derive it, but many of you may have seen it. And that's Bayes' theorem. So this notation is something I always also wanted to introduce. So this is actually the likelihood of X given Y. And this is called the posterior distribution. And often this is the one we want to find. So if you have a mammography machine, when you do a scan of the patients, you want to understand what is the likelihood of having cancer given a negative or positive exit from the mammography. And then the likelihood for the mammography is this one. And this is normally called the prior likelihood. And this term here functions as a normalization constant. The derivation of the proof, I don't know if, has anyone taken a course in statistics here? So then you've probably seen, who has seen the derivation of Bayes' theorem? Okay, that's roughly 50-50. So Bayes' theorem plays in statistics the same role as Pythagoras in geometry. It's an essential theorem. And what happens when you do Bayesian statistics is that you often have a model for this P of X and this Py of X. And you use that one to find a final distribution. So we will not put much emphasis on it, but I'm mentioning it here because you will see this popping up in many, many textbooks. And many textbooks take this statistical approach. So we will more focus on the kind of more frequentist approach. But when we move to generative methods, we're actually going to fit a probability distribution. And last year, we actually had a group of people who looked at generative methods and compare that with Bayesian statistics, just to see whether the probability distributions would match each other. That's also an interesting part. Maybe I'm opening up too many possibilities here. Yeah, I'm just going to skip this one. So what I thought of doing now is to give you guys a small homework. And that is, for those of you who have coded, so let me ask you guys, who has coded a neural network here? I know many has, no many. Okay. So the homework for you next time is just to bring back what you did. And then we can start discussing the implementations of it. But I will also, next week, I will go through the mathematics of a neural network. I see that we are getting close to the end. And then we are going to dive into CNNs and see how we can program that. And then recurrent neural networks. And then we do autoencoders till we reach generative methods. But for next time, I mean, go back to your codes for neural networks, whether you've done that, written a code from scratch yourself, or whether you've used the TensorFlow or PyTorch or other libraries. So that's the kind of homework. And I actually wanted to end with us presenting ourselves quickly so that we get to know each other a little bit more. And you should also state, if you can, what kind of topics you would like to study in this course. And then we take a break, and then we can continue after the break, and we can discuss possible paths for the first project, or just one project. Is it okay if we just go through now and you just do a short presentation of yourself so that we get to know each other, and then say something about your background and what you would like to do. Because if I know more about your background, it's easier to tailor the different lectures here. So I'm going to stop the recording. And for those of you online, we are going now to simply run through a presentation here.